So here's a wrap-up of this third view on the triple vector product or vector triple product identity. What we saw was that let's imagine you've never heard of the cross product, but that you've investigated rotations, especially infinitesimal rotations in three-dimensional space, then you know about this formula for the rotation of W by the bivector u wedge v, and that you know that that's exactly the right kind of data to specify an infinitesimal rotation. Then, if somebody invents the cross product or introduces you to the cross product and then says, oh my god, I understand the cross product, but I don't know what the heck this formula is about, you recognize this and say, well, wow, that's exactly what I've been doing all along with rotations. Okay, so a diagram of this is that rotations, infinitesimal rotations anyway, are labeled exactly by bivectors, or two vectors, things of the form u wedge v. And that's true in all dimensions. That's really the key thing I wanted to get across. Now, it requires the dot product to set this particular link up, but interestingly, it doesn't require any orientation. There's no right-hand rule convention necessary here. Okay, so it doesn't require the any kind of orientation or the right-hand rule, and I'll talk about that more in a little bit. But what's special in R3 is that a bivector can be identified with just a vector, basically by the Hodge star. Now, to be honest, I've been showing that in other videos in terms of forms, but the tilde transformation, which comes from the dot product as well, it lets you identify two vectors in two forms and vectors in forms with each other. And so then basically it's the star transformation that identifies two forms and one forms. So that's why you can get away with thinking, as physicists often do, of a vector as labeling a rotation. Now, if you actually talk to a sophisticated enough physicist, then they actually recognize there's a distinction here, even in R3. And again, it's because these transformations and the star requires the orientation. It all had to do with the volume form, and therefore really it's about the right-hand rule. The way physicists like to say it is, instead of talking about bivectors or two vectors here, they often talk about what they call axial vectors. And they note that if you take the cross product of two vectors, even if you think of it as a vector, if somebody changes the right-hand rule on you or puts it in a mirror, what's called changing the parity in physics terminology, then you're going to get the negative of the answer you had before. So they recognize that this really doesn't quite deserve to be called a vector in the same way as an ordinary vector does. Okay, so here's the perspective then that comes from both this view of the vector triple product identity and the previous one. It's that when you look at this combination, you want to really think of the two crosses as doing something different. Okay, so u cross v, whoops, not a hat, u cross v, that creates really, it's kind of a fake version of the wedge product of u and v. That we want something that's antisymmetric in u and v, but it's not really a vector. It doesn't behave in the same way in terms of dimensionality and in terms of orientation, things like that. And it's a label for an infinitesimal rotation. Infinitesimal, that's a long word. Okay. Then, when you combine that, when you take the u cross v, and then you cross it with w, that's really that rotation put into action. The rotation sort of labeled by the u cross v, and again, an infinitesimal rotation, acting on the vector w. So that's two very different roles for the cross, setting up a rotation and actually let that rotation act. If you combine them together, then you get this, which actually is a very, very natural way to talk about rotations, and it works in any dimension. Whereas thinking of these as vectors only works in R3 and requires a choice of rule, usually the right-hand rule, in other words, a choice of orientation. So that's a perspective that we get from thinking about the vector triple product in these ways. Now, I have to say, even though this is the wrap-up of the third view and the series was called 3 Views, I will do at least a couple more videos because I can't resist talking about a 4th view, which is quaternions. But that'll be a little bit.